Okay, welcome. My name is Gavin Nielsen, and this is the third session in a 12-part series introducing modeling, simulation, and analysis using the tools MATLAB and Simulink from the MathWorks. So today we're going to get into kind of the final aspects of introducing the environment of MATLAB, and we'll have finished hitting all of the high points of the language. There's certainly much more to explore, but after today it'll feel more like a lab where you can go play with things. So let's get started. Okay, so these are the 12 sessions laid out. We're in the third one right now. We're going to call this the Photoshop session, and we've already worked a little bit on context and philosophy and touring the environment, making a bouncing ball simulation, and then last week we did a piano modeling simulation and got a little further into the language, and today the big deal is matrices and higher dimensional arrays, and we're going to do some image editing. So that's kind of where we are in life. Okay, so today's agenda. So the first thing we're going to do is talk about a few modeling concepts, and then we're going to look at some language concepts, and then finally we're going to get into our project, which is kind of a light version of Photoshop. Super light. Obviously we don't have a whole bunch of time. This is a 2-hour session, so I'm glad you can join me. So without further ado, what is a matrix? And when I say the word matrix, you might be thinking of the movie, with Keanu Reeves. But what we're referring to here is the mathematical matrix. And what that is, looking at the little arrow there, it says a rectangular array of quantities or expressions in rows and columns that is treated as a single entity and manipulated according to particular rules. Okay, so this is kind of how we're not going to go into the depths of linear algebra and all the different rules for manipulating matrices and different representations of things. We're going to talk about it more on a conceptual level. But one thing I wanted to point out here is that the origin of the word matrix comes from matter or mother, and then you can see it kind of progressed through as languages have developed to breeding female and finally to womb. And so I think that's kind of an interesting thing. If you look at some of the other definitions, like definition 1 says an environment or material in which something develops, a surrounding medium or structure. Or number 2, a mold in which something such as a printing type or a phonograph record is cast or shaped. And so another way of saying matrix laboratory is like the mother object place of development. It's kind of an interesting it's an interesting choice of naming, and anyway, maybe I'm not sure if that's why the MathWorks chose to name it that, but it's a good name. So that's what a matrix is. It's a rectangular array of quantities and columns and rows, like you see there on the left. Okay, so how can we use matrices? Why do we care? One way of thinking about a matrix is a 2-dimensional array of values. And so, you can think about Microsoft Excel or something like that. How many different ways can you think of putting together numbers in that kind of organization? There's a lot of reasons you might want to do that. You could also think of it like a matrix as a set of vectors. Maybe like last week we had like I was saying, we can think of a vector as a matrix as a set of vectors stacked together. So like if you think about last week, we created vectors for different frequencies. And so maybe, each of those vectors for us last week was a particular note on a piano. So maybe we want to play 4 notes together. we could think of a matrix as a set of nodes, which is an interesting way to think about it. Like I said, you can think of a matrix as a set of equation constants, like constant coefficients in equations, and there's all kinds of fantastic applications there. You can think of it as sort of an organizational brick, just to throw values into, like a big set. It could be the basis for a surface. If you think about what shadow a three-dimensional surface casts, it's down in 2D. So we could store the heights of a surface in a matrix and represent the surface. If you look here at right, on the right-hand side, we have what's called a heat map. And that you've probably seen something like this before, but what this is it shows basically the frequency or probability that someone will visit a tourist site in Europe, which is kind of interesting. Obviously, Central Europe, and right in here, this is the hot spot, which is kind of neat. And what we're going to talk about today, which I think is one of the most natural ways to use a matrix, is as a model of an image. And so we'll talk about that. But there are so many ways to use matrices and two-dimensional, three-dimensional arrays, it sort of boggles the mind. So we're going to start in one place, and you can kind of go crazy as you need them. All right, so why don't we get into MATLAB, and we'll just try it a little bit. So first thing, we've already seen, creating a variable A. We've created some matrices, some vectors, right? There's a row vector. If we want to just declare, if we know all of the values we want to put in, we could put in 1, 2, 3. Okay, that's the end of that row. 4, 5, 6, the end of that row, and 7, 8, 9 could be the end of. Then there's the end of the matrix. So then when I hit enter here, we see we have a matrix. It's 3 rows tall, 3 columns wide, and those are the values in it. Like we say here at left, there's a few things that we've already used, like zeros and ones. These functions are designed to initialize matrices, especially when you're talking about large ones. More than, like here we only have 9 elements in the matrix. Let's say we want to fill a matrix 4 by 4 with zeros. I'm going to call this B, actually. There we go. Or maybe we want to fill a matrix C with ones. Maybe it's 4 rows, 5 columns. See over at right, 4 by 4, 4 by 5. Okay. I wanted to tell you about a helpful function. You may not need this unless you have gotten into linear algebra a bit. But in linear algebra, there's something called the identity matrix, which is usually represented by capital I, as in India. But within MATLAB, if you want to declare an I matrix or an identity matrix of a certain size, let's say we want one that's 4 by 4, we can say, we'll call it Q equals I, as in the eyes that can see things, and let's say we want it 4 by 4. Okay, and you can see that that fills and populates the matrix in a certain way, and an identity matrix has all zeros except for the main diagonal, which is all ones. So that's kind of the equivalent of, it is the equivalent. It's called the multiplicative identity. And so for a matrix, that's the identity matrix. So that's good. Now I wanted to talk about the transpose. So let's look at A again. And we have this 1, 2, 3, 4, 5, 6, 7, 8, 9 matrix. It's 3 by 3. But maybe I wanted to count down the rows and in other words, start counting here 1 and then 2 and then 3,
and then 4, and then 5, and then 6. How could I do that? So the transpose is an interesting way to do that. And I'll call it AT, A underscore T equals A transpose. You can use transpose just by the apostrophe. So what that does is it rotates the matrix. And so what was a row became a column, what was a column became a row. And if you can think of it as rotating the matrix along the diagonal. It also switches the dimensions. So for example, if I clear the screen here, if we look at C, we have a 4 by 5 matrix with C. If we look at C transpose, that's now C is 4 by 5, C underscore T is 5 by 4. So it reverses your size, and that's really helpful sometimes. Okay, good. So, higher dimensional arrays. If we think in MATLAB about the fact that we might want to hold data in more than 3 dimensions, and images are a great example of this because you might think of the rows as the vertical pixel, the rows as the horizontal pixel vectors, and the columns as the vertical pixel vectors. But typical color images have 3 components, right? There's a red and a green and a blue, RGB. And so for that kind of a structure, you actually need 3 dimensions. So you'll need the height and the width, and then 3 layers of that. So if you think of it this way, this little cube here is a three-dimensional array, and this would be 3 rows tall by 3 columns across by 3 colors deep. And what's also kind of interesting about MATLAB is that there isn't a limit, well, at least not a practical. There's a practical limit, but it's unlikely that you get there very quickly. So I can say A is equal to 1s, 3 by 3, and that will give me, let me do this a little bit bigger, 1s, 10 by 10. Okay, but I could also say A is equal to 1s, 10 by 10 by 10. I'm going to make this B, so we can see these. I could say that C equals zeros, 6 by 6 by 6 by 6. And you can see here, that shows that it's actually a 4-dimensional double. Double type, we'll talk about what the double means here in just a little bit. But we went from it showing the value to the vector showing what the size is, and that it's 2 by 2. And here we can see B is, or it's 10 by 10, but has 2 dimensions. B is a 3-dimensional array, 10 by 10 by 10. And C is actually a 4-dimensional array. So I can still ask the size of C. It just returns a vector that has 4 elements in it, 6 by 6 by 6 by 6. And you can really get that to be anything, like I say, for practical purposes, pretty much as many as you need. Okay, so we've talked about the transpose and how that rotates, but let's talk about permute real quickly. So permute is kind of the generic generic transpose. So whereas with A, let's make A equal to 1s 3 by 10. So if A equals A transpose, that will become 10 by 3, right? Okay, that's expected. But if we try to take B, which is 10 by 10 by 10, and put in the transpose, it will say, okay, you can't use that. It's not defined. You have to use the command permute instead. So the way permute works, and you can definitely go
go to the documentation and type in permute, and it'll tell you even more about different options. But fundamentally, permute says, let me make B equal to 1s, 10 by 7 by 4. Okay. So you can see when we rotate, it's sort of like rotating a Rubik's Cube around, but you can do as many dimensions as you need to. So let's just say we would like B, we'll call it underscore P, equal to B, permute B, and then what we do is we add a vector of how we would like the new dimensions to be. So right now, if we didn't want to change anything, we'd say 1, 2, 3. Let's just say we wanted to switch the third dimension and the first dimension. So we could say, in other words, sort of reverse them. We could say 3, 2, 1. Okay? I'll put a semicolon to suppress output. But now you can see how B permuted is 4, 7, 10 instead of 10, 7, 4. Okay. And that's useful for different reasons we'll get into. But those are permute and transpose and looking at things in a few higher dimensions. Alright, now we need to talk a little bit about sets. And I think this is kind of a comical way of talking about sets and Venn diagrams. So a set is basically a collection of distinct entities. You can think of a vector as a set, an ordered set, or a matrix as a two-dimensional ordered set. Sets themselves are not necessarily in order, but that means when you perform set operations on a matrix, you just happen to have them in order. And like it shows here, elements might be shared between sets. So what this is saying is that this cyan circle are all the people that are intelligent, and then this yellow circle is all those people that are obsessed. And if you're obsessed and intelligent, if you're in both, then you're a geek, or you might even be a nerd. And kind of, you can keep talking about it that way. So let's talk about set operations. Now, if we talk about geeks and nerds, the intersection of geeks and nerds, or another way to say that is the collision or the and, geeks and nerds. This is kind of a funny XKCD comic, people with strong opinions on the distinction between geeks and nerds. But that's one way to think about intersection, is it's the and or the collision. The union, another way to say that is the or the both, when combining sets, would be geeks or nerds in an inclusive sense, or both geeks and nerds. The complement is to say the other or the lacking or the not of a single set. So that would be, for example, if there was a set of geeks and a set of nerds, if I said anyone that's not geeks, then that would be everything outside of this circle. So there would be sort of a half crescent moon shaped slice of nerds left when I took out geeks. Okay, so let's talk about images as models. Okay, so for efficiency's sake, and you really can represent things in a lot of different ways, but for efficiency's sake, the way that images are typically organized is the canvas space is the matrix organization itself. So in other words, the vertical pixels, if you look at this picture here, you see this vertical row of these little rectangular cubes. Those would be the rows. Well, this would be one column of a matrix, and you can see the line up this way would be one row of a matrix. So the canvas space itself is kind of like the matrix. The element's appearance on the canvas is the value. So here it shows how these golden rectangular cubes come up out of the background, and so they're shown at a different level.
And that's a really good analogy because we can think of an image as a rectangular array of values. So, and those values are interpreted a certain way. And in this case, we can kind of think of it as there's the off and then the on. But if you think of grayscale or color, then there's a lot of different values that you could take in between. And here you can see how there's some higher and some lower values of heights from these rectangular cubes. If we think of the resolution of the image, that's the size of the matrix. So it's, 1,000 pixels by 600 pixels, 1,000 pixels tall by 600 pixels wide, or something like that. That's the size of the matrix. Okay, so let's talk, and I want to be very brief here, about array programming. And you can look this up and look into it more. If you look at Wikipedia, it says, in computer science, array programming languages, also known as vector or multi-dimensional languages, generalize operations on scalars to apply transparently to vectors, matrices, and higher dimensional arrays. And so MATLAB falls into that category of being an array programming language. And so we've already seen examples of this with vectors, how we multiplied by a certain number, or we did other operations. We used the dot operator to do an element-wise multiplication, I think. But this is going to allow us to be a lot more efficient with our time and with our code to get done the thing we're trying to get done. All right, so let's talk a little bit about languages. Not so much languages, all kinds of languages, but let's kind of improve our MATLAB vocabulary and learn a little bit about this keyword for. So we've used while loops before, but for loops are a very common type of loop to use inside MATLAB because of the fact that so many things are vectors and matrices. So I put a little sample of code here. Len equals length of vect. So we're assuming that vect is some vector, and we compute the length of it, so how many elements are there, and we put the value into len, and then we say for some index, so this is a new variable, equals 1 colon len. So what this is going to do is loop through this section of code inside the for and the end len times. So let's just say the length of vect was 8. It's going to loop through this 8 times for index equals 1, for index equals 2, for index equals 3, and so on. And it can do whatever it wants to on the inside. So what this allows us to do is quickly and concisely go through an entire vector element by element. And this is great for, we can multiply something through on a vector without doing this, but maybe we want to do something that's not uniform. So we happen to be doing something uniform here, but well, actually not. This is offsetting the index, so it's not exactly true. So I want to make a comment here that this is not as computationally efficient as the array programming, but it is more flexible. So there's a little bit of a trade-off, and you'll end up using this quite a bit. And so let's see a quick example of it. So let's get into MATLAB here. We'll clear what we've been doing, clear the command window. And let's just put this in. I'm going to put it in a script. Clear for my compact CLC. Vect equals 1 to 11. Len equals length of vect. For index equals 1 to len. And we'll say that vect, using the index of index, equals index plus 3.
Okay. So I want to also display what the vect, well, let's say it's going to be index plus 3. Let's run this real quick. I'm going to use the control enter so I don't have to save it. Okay. So we started from 1 and went to, we know there's 11 in there. See, we can see that it's a vect is a 1 by 11 double. And it started out being 1, 2, 3, 4, 5, 6. But what we actually put in it using this for loop was 4, 5, 6, 7, 8, 9, so on. So there's a real quick example of a for loop. Okay, so there's our single for loop and a good example. Okay, so with matrices, what's more common is to have a nested for loop. So here we can quickly create, now we're going to use the size function instead of the length function, and figure out how many rows and how many columns are in A. And then we're going to start an outer for loop, so this for and this end go together. And so the index, the variable I, is going to take the values from 1 and increment by 1 up to R, which is our number of rows. This is how big A is. And then inside of that, for each I, there's going to be a J. And J is going to look, starting at 1, going up to the number of columns, and then we're going to use I and J to fill this matrix with some values. So this way, if we use this kind of format, we don't have to know how big our matrix is. We can talk about any matrix without regard to how big it is. And that way we can also execute non-uniform operations. If we can't use array programming, it's nice to use array programming, but a lot of times we want to do something kind of special in here that you kind of need to know where you are. So let's look at that. Say this is A equals zeros. How about 5 by 3? Okay, now we're just going to follow the form of the code here. R and C are going to be taking the values returned by the size function. So R is going to hold the number of rows, C is going to hold the number of columns, and then we're going to use the for function. For I equals 1 to R, we'll add an n to that. For j equals 1 to C, add an n to that. And now we're going to assign different indexes. So for the ith, we're going to go along, and the inner loop is going to be going through the columns. So it's going to follow the like left to right, and then go down a line and go left to right. And we're going to use this to say the value that's held at that position is going to be equal to the column, or the row, times the column. So if we run this, now I want to look at A, see what's in A, see if it makes sense. Alright. Does this make sense? We have 5 rows and 3 columns, which is what we said. Now this value is 1 row times 1 column. That's the position. 1, 1. It's equal to 1. Second column, first row. First row, second column, that's going to be 1 times 2. First row, third column, 1 times 3, that's 3. Okay. Second row, first column, 2 times 1. Second row, second column, 2 times 2 is 4. Second row, third column is 6. So we can see that this is doing what we wanted it to do, but there's not a command that that will generate this for us. But very concisely, we can even edit this a little bit and say we want it to be 10 wide. Let's see what A does. All right, I did the same thing. So that way we can make these nested for loops to process a matrix or a two-dimensional array in a non-uniform way. Okay. All right, so the next thing we need to talk about is data types. So there's a few different data types. Have some examples at the bottom, but the three that we need to talk about today are doubles, logicals, and uint8s. So double stands for precision, for double precision floating point. And that means that a double, let me start here, a double or floating point type means that it's represented by a certain number of bits to give a coefficient. So it's, you know, some number point, a whole bunch of other numbers multiplied by a certain power of 10. So you can think about floating point numbers as scientific notation kind of numbers. Single is 32 bits wide. A double floating point number is 64 bits wide. Okay, then there's a logical type that we need to talk about, and that's really easy. It's either true or it's false, and that's the most basic type inside of computing. They're also called bools or booleans. And lastly, uint8, and what that stands for is an unsigned integer with 8 bits of precision. So integers are counting numbers, and when something's unsigned, that means we're assuming it's either positive or negative. Generally, it means it's positive. However your program uses it is whatever your assumption is. And the fact that it has 8 bits of precision means that it can take values from 0 to 255, which is 2 to the 8th, you know, the number of states it has times the number of bits you're using, 2 to the 8th. And we subtract 1 because we didn't start at 1, we started at 0. So anyway, those are our 3 data types, and the reason we're even talking about these today is because we haven't really dealt with them as variable types. In MATLAB, the double is sort of the de facto standard. If you don't tell it what you want, it's going to assume you mean double. And that is that way because it's a very flexible, easy to use, you know, it often stands for real numbers. Sometimes people talk about them as reals or real numbers. But we're going to need to talk about logicals, where the variable itself can only take on a value of 1 or 0, true or false. And then we're also going to talk about uint8s because, like we talked about before, images have 3 colors. Or a color image usually is encoded that way with a red component and a green component and a blue component at each pixel. And so they don't want to take 64 bits of precision to represent each of those colors. They usually take 8 bits of precision for each of those colors. Then there's 3 bits, there's three different colors, so 3 times 8 is 24 bit, is 24, and that when people refer to a 24-bit color image, that's what they mean. There's 3 8-bit components. So that's why we're going to use it a lot, because what we're going to import from typical JPEGs have 8-bit color channels. Okay, now, you know, we've talked a little bit the first time, the first day especially, we talked about different trade-offs there are in modeling. And so this is a great example. The stuff on the right is just an XKCD comic. It's kind of funny, but the stuff on the left is what we're going to talk about. And here we're talking about our size for these 3 different types: double floating point, unsigned integer, and logical. And so we can talk about the size of that thing, how much space it takes up, you can think of it that way, how accurate it can be, how fast is it to compute using. So the accuracy of a double floating point number is very, very high. It can be extremely high. But it takes a lot more power to compute double floating point or even single floating point, because you have to use a floating point unit, or you have to emulate a floating point unit in software. whereas an unsigned integer or even an integer can be handled in the ALU, or the arithmetic and logic unit. And logicals are like the easiest thing in the world for a computer to handle, because that's the simplest kind of logic there is. So the flexibility, though, for a double floating point, it's a general purpose, it represents real numbers. Unsigned integers, you tend to get more specific and more optimized, so that makes development a little harder if you're starting from an unsigned integer point of view. It's an easier place to project into instead of designing. HDR stands for high dynamic range, and what I mean there is that the double floating point, because of the fact that it uses a scientific notation style of representation, you can represent huge numbers or very, very small numbers just by changing your exponent. The unsigned integer doesn't have that kind of flexibility. It doesn't have a high dynamic range, because that's not the way that you're representing the number. So it has kind of a uniform precision or uniform dynamic range. And then the AKA is just also known as, I gave you some other things that people call these types of data types. All right. So now commands and operators. And this should take us to what we need through our project for today, of new commands and new operators within the MATLAB language. So let's start with the commands. So there's import data, and this reads in an image from a file. It can pull in a lot of different types of data. For us, we're going to use it to read an image from a file. Let's use that real quickly. First thing we're going to do is I'm going to copy some of the images, and we'll make a third day here. Paste the images into here. Okay. Okay. So I'm going to call it img, and then say import data, and let's pull in waterfall. JPEG. Okay. So if I run this, Control Enter, I want you to notice it created in the workspace a variable with the name img. It's a three-dimensional array. So it has 600 rows, 970 columns, and 3 color components. And the type is, like we've talked about, unsigned integer with 8 bits of precision. So each element of this is of that type. So because there are 3 color elements of that type, this is talking about a 24-bit color image. Okay. Now we have image and image SC. These are some new commands. I want to show you what it looks like when we try to plot, because we've used the plot command extensively, and that's a great command, and we'll still use it all the time, but it just isn't going to cut the mustard when it comes to images. So first of all, if we try using it, it says, well, you can't have more than 2 dimensions. So we're going to try, we'll say, just the red, okay? And I'm actually going to put this so you can see it better. If I just want to talk about the red channel, I can say that's the image. I want to use all the rows, all the columns, and just the first color. Okay? What if I want to try to plot just the red? Okay. I'm going to do this. It'll ask me to save. I'll call it test 1. Okay. So this is interesting. Doesn't look a lot like a waterfall though. So what this is doing is actually taking in all, we have this large vector that has, R now has 600 rows, 970 columns,
and it's plotting them all as if each column is a vector that should be plotted here, which isn't the way we really want it to be done, right? So what we really want to do actually is use the image command. That looks a little more like a waterfall. Okay. Now you might be asking yourself, well, this is kind of weird. Why do I have the numbers here? That's because we still have our axis on, and you also notice that it's stretching the image around in a way that we probably don't want it to. So there's a couple things I'll add at this point just because I think it's easier to think about now. So we'd like to add a few other commands to image. One of those is axis off. Well, let me actually execute them here. And that'll turn off the numbers and the little part there. We can also turn on axis image and axis ij. So what doing those two things does is it maintains the aspect ratio. So it'll only plot at the size that it can do it at the largest, in its largest dimension. So that's useful. Very good. Okay. Now what's this image? So that's image as a command just displays RGB colors, or RGB images. Image SC gives us a little more control. And what's really useful if we're talking about something that, well, let me show you. Let's use image SC, and we'll put axis image, axis ij. Okay, this looks about the same, right? But what if I want to interpret? I think I can do this with, yeah, I believe so. 0 to 200 instead of 0 to 255. It may not let me do this with an RGB image, so bear with me here. I'll try 100. Yeah, it's not going to let me do that. So let's talk about the just the reds in this image. So if we say the red, like we talked about before, all the rows, all the columns, and the first color channel, we can use image SC to look at that. And this is showing us a rendering of the red color channel. And you might be asking yourself, why on earth then is this blue and yellow? Well, that's because of the association that it has with different values. So I'm going to turn on the color bar, and that's going to show you that for a value of 0, that it's showing you a dark, well, basically a black or super dark blue, and then for a value of 255, it's interpreting that as a yellow. We can actually change this around though by using different color maps. So this is the default color map, I believe, right? Yes. So we could make it a winter themed color map, or maybe we want to talk about it in grayscale, or maybe we want to talk about it using the jet color map. So there's a lot of different ways to interpret the data. This is just happens to be the red channel though. We could, by the same token, look at the blue color channel. All the rows, all the columns, sorry, RG. Let's look at the green color channel. It's a second. And G. Okay, so that has different intensities. If you think back to that image, it had those cylinders are up to a different height. So image SC lets us look at this differently, but we can actually
say right now it's going 0 to 255, but we could actually interpret, so anything that's 200 or more is going to be red. And this lets us kind of zoom in on the stuff we're interested in. Maybe we want everything below 50 to be dark blue. And you can see how you can really get to know your image and analyze the data in it very quickly and concisely by using these custom scaling. So we're basically telling it how to interpret an image by telling it, you know, here's your color space, or your color map. Let's say it's gray. And where's the low, where's the high? Because we might be using a double, and we might want the double to be between 0 and 1. This happens to be an unsigned integer, so we want it to be, you know, probably 0 to 255. So, okay, that's enough about that. So that's image and image SC. We've already talked about permute. The last one I wanted to talk about was class. Class returns the data type of the variable. So let's say we ask for the class of G. That tells us, oh, that's a uint 8. If I just made a variable called A equals 4 and asked for the class of A, it'd say, okay, that's a double. And then finally, if I said let's see, what are we going to call this? Call it B. Let's say B is equal to A less than 2. Okay, so A has the value of 4, and I'm asking a question, is A less than 2? So the value of B is 0, but it's not 0 in the double sense of it. It's actually 0 in the logical sense. So if I ask, what's the class of B? It's going to give me the return logical. And you have to remember that MATLAB is the dynamic language, so if I say B equals 1, it doesn't change because that's an allowed value for B. It's still a logic. Oh, excuse me, it did change it. What it would have been better was to say B equals true. And then if I asked for the class of B, then that still returns logical. But what it did there just a second ago was it said, okay, if I assign a value, B equals 3.3, and then ask for the class of B, it dynamically changed the type of the variable. So that's something to keep in mind, that it doesn't stay illogical if you reassign it to something that's not illogical anymore. All right, so let's talk about the operators. We've already talked about the transpose a little bit. Let's talk about the complement. So let's say B equals false. So maybe I want A to be equal to whatever B is not. So I'll say A equals not B. So then A equals 1. Maybe I want A to flip back and forth. So maybe I want A is equal to not A. And if I do the same thing again, now it's 1. So it could alternate back and forth. So if you have a defined set that's larger than 2 elements, you know, then you could define what the complement of a set is, or if you have other sets that would make more sense. For doubles and integers, well, I'll show you what it will do. Let's say we have V equaled 3.4. If I take and ask for the complement of V, that's interesting. It says the complement of V is 0. And class of A and S is logical. So basically, that doesn't do us a heck of a lot of good. You would think but if you stop and think about the representation of a floating point number, there's more than one way to say 3.4. But yeah, it's just not a good question to ask. I guess MATLAB did have an answer, but not one that really made sense from my point of view. Okay, that was the complement. Really useful for things like logicals and defined sets. All right, now we've already seen, I believe, the relational and, which is double ampersand. So let's have let's clear this out. A equals true, B equals false. C equals A and B. So this is saying if both A and B are true, then C will also be true. And since B was false, C is now false. So that's the relational and, but we would also like a set-wise or an element-wise and that's the single ampersand. Okay, and by the same token, the or is a single bar or a double bar, depending on whether you're talking about set-wise, element-wise, or relational. So if I said the same thing, C equals A or B, the answer is actually 1 now, because one of those was true. But if I had a larger, let's say A was equal to I don't know, 3 by 3, and say A equals A times 3, so now it's 3's down there, down the diagonal, and maybe I want to know let's see, well, we'll come back to this. This will make more sense when we look at the sets together. But we can use these set-wise relationship things to say what in the matrix of A is greater than 2. And so this actually, our answer returned us a logical answer that was 3 by 3 elements in size. And it said, oh, well, here is the matrix that shows you true where your query came back as true. So it was on the diagonal, just like we expected it to be. Alrighty. And with that, we're ready to get into some cool operations and Photoshop stuff. So the first thing we're going to do is line up a bunch of different operations. And like we mentioned before, the first thing we've got to do is open up the file so that we can load it in. And it's important to remember what MATLAB is abstracting. If we think about a JPEG image, there's an encoding standard, there's metadata like the GPS coordinates of when it was of where it was taken, the time it was taken. You know, it might have tags on it. Maybe even parts of like what the shutter speed was, things like that, metadata that we want to ignore because we just want the data. Then there's compression standards that make it smaller and easier to throw around that we also need to decompress from. So we'd spend a long time if we had to do all of that by hand. So we're going to use our import data function, and then we're going to abstract that in our own function just because I'd like to call it something more specific to images than import data. Okay, so let's go back to MATLAB, and I'm going to write a function, and it's going to return an image, and it's going to be called load image. And I'm going to give it a file name as an argument. So I made a little comment to myself there. So I want return image to be equal to import data at that file name. Nice and easy, right? So it says, is that what you want to call it? Yes, that's the name of the function. That's what I want to call it. Okay, very good. So let's just make sure that works. Load image. I'm going to do it this way. It's a little bit easier to read. Okay. Alright. So now we have the image. Maybe we want to abstract the display of the image. So I want to point something out real quickly that image already does for us. Let me do it this way though. Basically, when we talk about a typical plot, the origin is in the lower left corner, and so higher numbers get plotted higher, larger numbers on the x-axis get plotted to the right. For an image, the origin is actually in the upper left corner. So increasing rows actually are down on the y-axis. Increasing columns are to the right again. That's for images and video. So this is automatically flipped by the image function, but I would just want to show you. If we look at this and say image img and run this, sitting behind us, here it loads. But if we turn our axis back to XY mode, it's upside down because the order is, this is the way an XY plot would typically be ordered. So if we turn axis back to image and IJ, then it flips us around and gets our aspect ratio right. And then we also obviously want to turn axis off again. So let's abstract those functions. There's a few quick ones here, and we'll call it function plot image, and we don't need a return variable. We just want to give it an image, and we're going to use the image command, and then we're going to use axis ij, axis image, and axis off. Okay, save that. Plot image, please. Just let me close it, and I'll do it again. There we go. So now we have a way to display the image that we can see what we're doing. Okay. So, like we've already actually gone through the image SC stuff. SC stands for scaled color. So we can change color maps, we can change scales, all that kind of stuff. The rest of this we've already done, so we're doing great. Now, the first thing I think that's useful to talk about in terms of processing and manipulating images is thresholding. And so if we talk about an image, we can quickly look at a threshold and say, I'm curious to know, like in this example on the right hand side, there's a matrix A. And maybe there's a threshold T that says, give me all the A's that are less than 4. Maybe there's another threshold T2 that says, give me all the A's that are greater than 2. And then here on T3 we get to use this set-wise or element-wise relation and get to see what's both in T1 and T2. And so a few things to think about as we're doing this. First of all, T is always going to be the same size. It's the same number of rows and columns as A. Because you're asking a question about A, And so it has to answer that question for all the elements of A. So when you're taking the AND command, these also need to be the same size. Okay. So let's do this real quick with our image. And I'm going to make this part of figure 1. And then that's the threshold, this sucker. So let's use the red channel. Well, we could use all the channels, I suppose. Okay, let's use all the channels. And so we don't have to, we can still look at the whole thing this way. Let's say that we're going to make a variable called thresh, and that variable is going to say all the image that is, how about greater, so we're going to look at the highlights here. We're going to take out the load things. So how about greater than 50? So I'm going to run this so we can look at what thresh is. So here it puts this up, but thresh is of type logical. See here? So if I try to say figure 2, set it off to the side, plot image thresh, it's going to say that's interesting. It doesn't know what to do with that. Let's just try using image. Yeah, that's what I thought. So what we need to use is image SC to view this. So let's try that. Image SC thresh. Oh, that's what. There we go. I was calling it the wrong thing. I apologize. I don't think this is going to work quite right. We'll go to figure 2 here. Turn down my volume so that it's not so annoying. Okay. So this is interpreting all the things greater than 50. Otherwise, it's putting in black. So let's say, and actually, it's okay. So let's think about this for a second. If we use image, we really need to talk about this in terms of a single channel. So let's talk about just the red channel equal to all the rows, all the columns first, and then we'll say red greater than 50. Image SC red. So this is displaying a logical variable, so it's either on or off. And you're saying, oh, this looks kind of like there's gradients, right? But what if we change our color map to gray? Actually, if we zoom in, these are all either black or white. I believe they should be, yeah, because we're plotting. Oh, sorry. My fault here. This should be thresh. There we go. So this is either black or white. We're saying everything in red that's greater than 50. What if we said everything that was less than 50? We should
It should be the complement, right? Yep, it's the complement. So let's just verify that. So if this is less than, greater than 50, what if we just use the complement there? Sure enough. So we reversed all those values from 1 to 0. Okay. Why don't we take this and write a function? So something that has a minimum red, a minimum green, a minimum blue, minimum red, maximum red, maximum green, maximum blue, and that way we can filter the function a little differently. Okay. So let's write a function. Return image equal to thresh all. Okay, and I'll use the next line, ellipsis, dot, dot, dot. So thresh all, and we'll have r low, r high, r green low, and green high, and blue low, and blue high. Okay. So all we have to do here, this is actually pretty neat. All we need to do is say, let's first get the size of this thing. Let's see, do we have to do that? Actually, we don't need to do that for this one. We can say that red is equal to all of, we have to hand in the image first, don't we? There we go. So image, everything, okay. Now, the red threshold is equal to red, let's see, it would be greater than red low and red less than red high. That makes sense? So then we can say that blue, by the same token, is all the rows, I always do that, green equals the image, all the rows, all the columns, second color, so RGB. And the green threshold is green, all greens greater than the green low, and all greens less than the green high. And blue equals image, all rows, all columns, by 3. And let's see here. The blue threshold is equal to blue greater than blue low, and blue less than blue high. And then finally, I'll make a little more room here. The return image equals red threshold and blue threshold, and red threshold, green threshold, and blue threshold. And that's it. And this way we can filter an image pretty quickly and easily using the RGB color space. So this is thresh all. Hit save. Alright, so let's try this in our little test here. So thresh equals, so let's just say, if I run this real quick, thresh equals thresh all, and let's say we're going to hand it the image. Red low will have kind of a small, let's see if we can get most of this stuff, right? So we want kind of a high red value.
So let's make the low part of the red threshold 200 and the high part 255. And then we'll make green all of them and blue all of them, 0 to 255 on both of those. So image SC, thresh, and color map, gray. Okay, interesting. So maybe I could even crank this up a little more, huh? How about 225 to 255? Or a little less. 100. It's interesting what trying to pull out thresholds in different things. You can definitely notice how, looking at these two images, how the lighting has affected, even though her skin is pretty consistent. Notice how the lighting has affected this color space. And so we're thresholding based on RGB values. But you might want a threshold using something like hue saturation value, HSV, and you can convert to that color space. We won't get into that today though. All right, how are we doing on time? Okay, got about 50 minutes left. So let's take the next step. That's thresholding. We can do that for all kinds of things. Let's talk about spatial derivatives. Okay. So spatial derivatives are kind of interesting with images because of the fact that when we typically think about derivatives, we typically think, well, let's see what Google thinks first. We typically think about some time series maybe. Is Google Images going to prove me wrong? Yeah, well, this is, there we go. So derivatives and integrals. We typically think about like the tangent of some function, and so it's a function of one variable. But a spatial derivative in 2 dimensions actually has a lot of different potential derivatives. So let me explain what I mean here. If we talk about a set of numbers, I'm going to open up Excel real quick to show you this. So 1, 2, 3, 4, 5, 3, 2, 1, 1. Just do this kind of quick. Okay. All right, so let's just pretend these are the values of pixels that we're talking about, okay? And we'll make them kind of uniform size. All right, well, let's think about this together. If I want to know, let's say I was just talking about this vector, then the discrete derivative is a straightforward thing. It's just the difference. So let's say I'm talking about, the difference between 1 and 3. Well, then there should be kind of a 2 on that line right there. And then the difference between 3 and 6, there should be a 3 on that line. But with respect to this number in the middle, maybe I approach it from the vertical dimension, the vertical direction. And so here, there's only a difference of 1. It went from 2 to 3. And here there's, so but what if I come at it from the side, like a diagonal, or this diagonal? And so you can think about it, there's actually an infinite number of directions you could come from. But it makes it kind of interesting because there's more than one way to define the spatial derivative. What we're going to do is just, because for a lot of
for a lot of situations, it's okay just to look at it in one. We'll talk about it just as the vertical. Talk about just the vertical columns. So let's run that real quick. And why, you might ask the question, well, why are we even messing with this? Why do we need to write a function? What's the purpose of a spatial derivative? Well, if we think about what the values are here, they're values of color or values of intensity. You know, maybe it's a grayscale image, so it's how much light or how much dark. We can actually see where edges are in the model by seeing when the derivative changes quickly. So by calculating the derivative, you can start to detect edges in your image in kind of a gradient form. So that's why, or one of the reasons why it's interesting. So what we're going to do here is write a function, and we'll call it return image. We'll call it DDR for derivative with respect to rows, d over dr. And we'll say that we just need to give it an image as an argument, as an input. All right, now let's we'll ask for the size function, but we have to remember we also have the number of colors too. But we won't call it K, let's call it G. So when we ask for the size of the image, it's going to return three things because it's a three-dimensional array. So we'll have a place to put it there with the G, the number of colors. So we'll write a for loop for I equals 1 to R, for J equals 1 to C, end to end. All right. And now why don't we make return image equal to, we'll have it all be 0. We're going to pre-allocate it. So it's, and you got to remember, when we don't tell it what type, it's assuming we mean a double. So our return image is actually going to be a double. Okay. So let's take this, and we want to calculate our return image for I and J. What do we want this to be equal to, though? So we want to look through. Let's say this is the ith and jth. So we're maybe I is 3. We're going 3, 1, 2, third index down, and J, third column over, so 3, 3. So we want to look back 1. So we want to look into image and say I minus 1 minus image I, J, right? But you have to remember that it's a three-dimensional thing that we're putting in. We're putting in the colors. So we actually need to tell it which color channel we're talking about too. So for this one, just to keep it simple, we're just going to average all 3 color channels. So, and we have to be careful about one other thing. Since I used I minus 1 right here, if I start at 1 and then I subtract 1 from it, I won't actually be on the image anymore. So I'm actually going to make I starting at 2 to R. So that way the first one, we'll ignore the first column. We'll ignore, we'll ignore the first column. Okay. So what we need to do this for each color channel. So I minus 1, J, 2. So there's a second color channel. I, J, 2. And then the third one. Oops.
Now, this is going to give us a relatively large number, but I would like to average them. So I'm going to take this and divide by 3. Okay. And then I know that the average can't be any higher than 255, so I'm going to reinterpret this. Well, we'll do that at the end. Right here, return image equals return image divided by 255. So this return image is going to be defined between 0 and 1. Okay, very good. Let's save that as DDR. Okay. So why don't we go into test. And let's display, let's take the derivative. Okay, this will be figure 3, and we'll just call it D equals DDR the image, and we will say image SC, D is our new image, and we'll interpret that from 0 to 1. Okay. Let's run this and see what that looks like. There's figure 3. Color map jet. I'm going to make D larger. So D times 10. Maybe times 5. I got chicken. Okay, so I can see that's interesting. It's increasing, and there's a lot of changes as we look at this. It looks like the quilting, the pattern of this makes for a lot of quick changes, right? Whereas her skin is relatively smooth. It has much lower. If we make, this might be a little easier to see as lines if we make the color map gray. There, that's a little bit easier. So now we're looking at an intensity of gray. So you can see how these intensities are actually values that we can go ask, well, what is the value there? It returns, because it's an image, it does return 3, like a triplet, but because we're only interpreting one value, they're all the same, 0.313. And then as we move out here, they're much lower. Looks like this is 0, 0, 0. And maybe if we can get onto a gray one, maybe like right there's a gray one. It's 0.1, and then these whiter ones out here are up at 0.9. So that's the derivative, and we can, why don't we try this for a couple of other images just so that you can get a sense for how this works. Let's use mug1 image. Alright, so that's color map gray, make this color map gray too. This actually is a little bit easier to see kind of the strokes of the pen. It's an interesting mugshot.
let's turn on axis ij and axis image and axis off. So you can see here how these two pictures are related, and why the derivative might be interesting if we're trying to figure out like the shape of an eye, or maybe the overall outline of her head. You know, you can see where her hair changes. It's a color change abruptly from the gray background, and you can even detect things like her shoulders. It's a little more faint here. So one thing I want to point out too, her shoulders, that's almost a horizontal line, and we're going to, or excuse me, it's we're going down. So we'll do best at horizontal lines. I think it's just because of the shadow. The transition isn't very sharp there. It's probably, yeah, we can still see it. It's just smaller. But yeah, so that's what derivative looks like. Okay. Now, I think we have, yeah, so we've got about half hour left. Sorry about my Facebook stuff coming up here. Alrighty. So I want to show you a little bit about morphological operations, and then we'll do the GUI. So let's take a look at that. There it is. Okay. So morphological filters. I think that's a great word, morphological, a good one to look up. But there's two key morphological operations. One's called erosion, which we'll talk about first. And what erosion does sort of eats away at the border of an image. So you can talk about it within the context of grayscale images, but we're just going to talk about it in terms of logical images. Okay, so at top we see it's just zeros and ones, and I color coded it so that you could see better what was happening. Basically, what's going on is the outside, if there's any cell or any pixel that's touching red, that becomes red itself when you erode. So here you can see all the twos. I showed you the twos because that's what's going to change into a zero. Okay, so it eliminated all these little guys, and it took the one back down all to itself. And that's called erosion. Okay, dilation is the opposite. Dilation grows every border out from where it is. So in dilation, if our original image is this green, all these little pieces, and we dilate it, then every bit of red that's touched by the green becomes green. So then that gets bigger. And you can see here's the twos. This is the change. All these things become twos. And these were at least one away from any contact. So it kind of it inflates it, or it dilates it. So like I forgot to mention here, with erosion, it tends to eliminate small spatial blobs, and blobs it actually is the technical term, but these guys are going to get eliminated. This was big enough so that there was a center part to it. So with dilation, what this tends to do is to fill gaps. So you can see how it actually connected all of these guys together. So these gaps that were in here got connected. So when you combine them, you can do some interesting things. And when you combine them in one order, of erosion followed by dilation, since they're duals of each other, that's called opening. And what opening does is tends to get rid of small blobs. It's a spatial type of filter, or a spatial operation. So we see that here was our original image, and then we eroded it, and that's what it looked like after the erosion, and then we dilated it. So here's our original and then our opened image. So it filtered this to create this. Closing is exactly the opposite. This tends to fill in small gaps and holes. So it's the sequential operation of dilation and then followed by erosion. So here we can see our original, we dilated it, and then all this was this way, and then we eroded it. And it ate away a lot of that, but here is, in this green, is all the stuff that we kept. Okay, so why don't we, I think we have time to do this. It won't take, this actually is pretty easy. So we'll write a function called erode. I'm going to call it erode1. And it's going to have a return image. We'll pass in an image. And so we'll do the same old thing we always do, but we only have to have R and C because we're only going to pass it binary images. And then we're going to say for I equals 2 to R minus 1. So we're gonna not worry about the outermost pixels. So we're gonna start at 2, and we're gonna go all the way to the end, and then come in 1. That way we can look around and not go off our. We don't want to fall off the map essentially. For j equals 2 to c minus 1, same thing. Okay, and we know that our return image. Just start off at zeros, R and C, but we don't want this to be a double because it's just it's a waste for one. But so we'll say it this way. We'll actually convert this, or cast is what it's called, this to a logical type. Oops, there we go. Alrighty. That'll still work fine. Alrighty, so what we want to do, look to see if there is anything false nearby, and then erode if there is. So here we just need to say if, we're just going to have a few different if statements. If, we'll look at the image ij. So first we'll look backwards, we'll look upwards one. I minus 1j equals false. Then return image ij equals false. Else, if, okay, so we haven't talked a lot about else ifs, and I'll leave it to you to look it up in the documentation, but this is basically, if this is true, then do this and skip the rest. But so we'll basically have a set of else ifs here. Else if image, and we're just going to kind of look around it. So that's the one that's above. So let's go to the upper right corner, j minus 1 equals false, then return image ij equals false. Else if image, now we're going to go to the upper right, so this is going to be I minus 1, j, oh sorry, I think I did this wrong. I minus 1, so this is upper, this should be upper right. Now I want to go to the right of it, so j plus 1. If it's equal to false, then the return image ij equals false. Else if, okay, now Now we want to do the same, let's see. Sorry for messing you up here. So this is above it and equal. We want to stay above it and to the right, and this one is next to it to the right. And then you want to be below it, so j plus 1, excuse me, I plus 1, j plus 1. Then that makes this false. Oops, put a semicolon. Okay, that was lower right hand corner. So now we want to go directly below it. I plus 1j. If that one's false, then this will also be false. Now if we go also lower and back to the left one, if that one's equal to false, then this is going to be false. Forgot the semicolon. Okay, so this is lower left. Now if we just do just to the left, not lower. It's false. And last one, else if I minus 1, this is upper left, j minus 1. If that one's false, then the return image is false. Okay, great. So we'll save that. I'll call this eRoad 1. Very good. All right, let's test it quick. So let's test this real quick. So we'll go back to our test 1. Let's actually save and make a test 2. So there's our original. I guess it isn't getting that big, but right. So right now, sorry. See. So here's our road 1, and I want to make a test. Here we are. Test 2. So there's our thresholding. So I just want to look at the derivative, and then we'll erode the derivative a little bit. You can see how this works. So instead of making a figure out of this, so I'm going to turn this off. Well, no, we still want this derivative. But we'll make this figure 2. So you recall we just loaded it up and plotted it, or plotted the image, and then we look at the derivative. Now let's now we'll threshold it, the derivative, and that's easy. So we'll just say the derivative threshold dt equals d everything greater than 0.3. Okay, and we'll make this figure 4. Image SC. Now we want to talk about the derivative threshold, and I don't think we need to set the range, so it'll probably do it automatically for us, right? color space for this, gray, or color map rather. Okay, so you can see this took all of the values. This was a grayscale image, remember double type, and this said make it white if it's within this range, otherwise make it black. Alright, so if we look at this, and look in at her eyes, we can see actual values here. And we can move one and, you know, see how big these are. Okay, so let's try eroding this by 1. So we'll go here. Now erode this by 1 pixel. So dt erode equals erode 1 dt figure 5 image sc dt erode. Color map gray again. Oh, you know what? We need to add to our little erosion one quick thing I forgot. My fault. These actually need to, instead of starting with logical and everything being false, we never set it to anything being true. So we should actually start with return image being equal to the image. And then we only check these things actually, we don't even have to worry about that. As long as we have it starting as the real image, then if it's touching okay. So then we'll say if the image ij equals true, then do these things. So in other words, it's not going to actually check to see if it should erode unless there's actually something there. There's actually a true value to work with. Okay, sorry about that. Let's look at test 2 and rerun that. Alright. So you can see how it was only the larger masses that survived. It sort of decimated this. Now, let's try dilate and see how dilate works. What's nice is we don't have to write this whole thing again because it's a little bit of a pain, but it's not complicated code. It's just there's a lot of it. So we'll say this, save as, and we'll call it dilate 1. Okay, so this starts here, and with this, we want to check basically the opposite. So if anything, we want to check and see first if we're talking about something that's not already true. So we want to check and see if it's false. If the image that we're analyzing is false. Let me say this differently. If the pixel, like any of the black area, let's zoom in so you can see what I'm talking about. If we're in the black and we happen to see something next to us that's white, then we want to be white. So we first say if that image ij is false, and if the thing next to us is true, then make us true. So all we really have to do here is replace false by true, and we replace the true by false at the top. You can see that these are mathematical duals. It's kind of interesting, I think.
just copying and pasting true in here. Okay, very good. So this is called dilate one. And then this error will go away. I'll hit save. Now let's go back and go to our test 2. And instead of using erode 1, let's use dilate 1. Run that. Okay. So you can see how all of those things just grew. And it kind of made the little specks become bigger. And it made the areas that had already had something in there become larger. See that? So it grew them out a little bit and closed the gaps. So now this is where it gets fun. Now we can add in some cool stuff. So we can add a function called dilate n. Return image equals dilate n, and this will, for n times, it will dilate it out. And it's really easy to do this, so we just need to add it an image, give it an image, and say n times. And so here, all we do is, again, RC equals size of the image, and so what we'll do is for, let's see, we'll call it h equals 1 to n, for I equals 1 to j, 1 to r, for j equals 1, wow, j equals 1 to c. So it's a triple nested for loop here, and we're just doing the outer loop to continue this idea again. So this is kind of neat. So now we can just call, this is dilate n, so we'll save it as that, dilate n, and all we're going to do, oops, actually we don't even need all this stuff, I'm sorry. All we need to do here is call dilate image, and we'll say that image is equal to that. So this is going to dilate itself over and over and over n times. So no problem. And then we'll do exactly the same thing for erode n, except this time, obviously, change the name of the function, erode 1. Yeah, this needs to be dilate 1. Good. All right. So now let's try this. Now that we have these guys, we have, let's go back to test 2, and we can say dilate 2, or excuse me, dilate n by 2. Oops. Ooh, did something too fast, huh? Let's change that to morph since we changed what that was. Return image. Okay, so it did not like dilate. Let's just figure out why real quick. Dilate n. Oh, we forgot to return, didn't we? Huh, my fault. Actually, all we really need to do here is say return image equals image, return image equals dilation of return image. There we go. And the same here.
That should do it. Back to test 2. Alright, now we're seeing that we're actually able to really make this a lot more fat, I guess you'd say. We're really starting to look at the blobs. So this is with 2. What if we make it 3? Okay, let's check and see if erode works in the same way. Erode n. Basically got rid of everything. And so the last thing we want to do is add open and close to our little toolbox. So we'll call this function return image equals open n, and all we do here is feed it an image, say n, and then we say return image equals image. And actually return image first equals, let's see, so opening, let's check out our notes here again. Opening is erosion followed by dilation. So return image equals erode n of image by n. Dilate n. Now we want to dilate the same thing that we eroded. So we're going to dilate return image by n, and then we're done. So this is called open n. Alrighty, so let's go back to our test. So I'm going to close some of these because we have a lot of things open. We don't really need all of them open. Okay. So let's try open n. Okay. What if we open 2 instead of 1? That filtered everything out. Okay. So now we have open n. We can actually make this close n also. Close n, and we just need to do these in the opposite order. So return image equals dilate n of image with n, and then return image equals erode n, the image, and n, and that'll do it. So I can get rid of those. Great. And close n actually I think will be more interesting to look at. Too much? 2? I may have. Did I forget something? Oh, yes, this should have been returned. Sorry about that. It's test 2. There. Okay. Now, I want to just kind of know what this looks like. So I want to show you, as we alter this, let's try 3 pixels, how this affects our image. So it's a different kind of spatial filtering, but we're kind of we're closing up gaps. Is sort of the type of operator this is. If I use 4 pixels to close gaps, you can can see how that affects, and we can actually start to block out, get an idea where the eyes are and other things. Okay, so that was great. We delved into a little bit of little morphological operations, which is cool. And we did a little spatial derivatives. Got to use that. Okay. So now we already did logical extensions to n levels. I just want to make a note here that the more, I guess you'd say, correct or technical way of doing this is not to go out by one pixel, but to use structuring elements. But I didn't do that because it takes longer to talk about in the way I think about it. So if you're interested in this stuff, go read up on structuring elements for erosion and dilation, and you can get more sophisticated. Also recommend the book by E.R. Davies called Machine Vision. That's an excellent book on the topic. Okay, so the last thing we've got to do, and we have 5 minutes left, I think we'll go a little bit over, is just to look at building a quick GUI with we've actually built up a lot of different operations now. So to build a GUI in MATLAB, there's two different ways. One's using the guide tool, and the newer and easier way is using the app designer. And so we're going to talk about the app designer because that's an easier way to get introduced to it. And then, yeah, we'll go from there. So the command to open the app designer is, like you'd expect, app designer. And there's two views that are two ways of looking at the same thing. There's the designer view or the design view. It's either called design or designer. We'll see in a sec. And then there's the code view. And so the design view is like a kind of a preview of what your final thing is going to look like. And then the code view is the code that's behind. Often in modern IDEs, they call it the code behind. So those are two different ways of looking at the same thing. And actually, it's kind of a nice introduction for our Simulink stuff next week. That Simulink is just a graphical way of thinking about stuff you could write in MATLAB. But we'll stay focused on the GUI and not get into the philosophy. So the things to remember, elements that we want to talk about for the designer, the app designer, is first of all components. And components are objects that populate the design surface, like buttons and edits and sliders and plots and things like that. And so components are like an element that you could interact with. A callback is an event that happens in response to what a user might do with a component. So in other words, if you clicked, used your mouse or your finger or whatever and pressed a button, that would generate a callback, or in other words, an event that would get triggered. And so when you want to respond to some event, like in other words, you want something to happen when someone presses a button, you create code that runs for those callbacks. So let's just see how this works. All right. Let's clear this up. CLC. Now, so we use the command app designer. And that will open up this new interface. Okay. And there's some tells you a little bit about what's going on, and you can click on some links it'll tell you about the differences between app designer and guide. Like I mentioned, those are kind of the two ways to build things. So I'm just going to say OK here. All right, so what this is that we're looking at right now is the design view, and we can click here to go to the code view. So right now, just it being blank as it is, this is what code is behind there, and we can't actually even edit it. We can put the cursor in and highlight things, but I'm trying to type here and I can't. I can't delete things, and that's kind of nice actually, because this is automatically generated code, and we can't
can't mess with it, and that's good because we can't mess it up. So if we go back to the design view, the first thing we want to do is add a button. So what we'll do is drag a button from the component library and put it on the design surface. So we can change the name of the button, and I'm going to call this load image. That's the first thing we need to do, right? I'll change the name. So this is the text that's on top of it that the user sees, and here's the name of the button. So I'm going to call it app.load button. All right. Now it doesn't know what we want to load, so I'm going to put, and I can resize this stuff and make it bigger or smaller, whatever I want to do. I'm going to call this file name. Okay, so this is what's going to allow us to put in a name, and we'll call file name. We'll split it up and we actually save it there. Okay, now I'm going to save this, and this is it all gets saved in the extension type .mlapp, MATLAB app. So I'm just going to call this photo 1. Okay. So now that we have a place to put the file name, I dragged an edit field of text type, so it allows for text entry over here. Now I'm going to right click on this. I'm going to go to callbacks and add push button, add button pushed function callback. And it says, do you want to call it this? And we can change the name if we want, but that's fine. I want to keep that. Okay, now you'll notice how there is a little white spot. Most of this is grayed, but then it's white. So in the white spot is what it allows you to write in code. So here, we can say, we'll call this file name equals app. Well, why don't we do it this way? We've created a function called load image, right? So why don't we call that function? We'll put it in a variable called image, and we'll say load image app.filename.value. So what this is going to do is go and look at what's in the object app.filename, which, just to remind you, is this little box. It's called app.filename. And the value is what's being held in there. So if we put in the name of a file, it'll get loaded into that value. Okay, if I hit enter, then I want to prove that we loaded it. So we'll call plot image. So I'll save this and I'll run this. Fail.jpg load. Cool. So this is working. Mug1.jpg, waterfall.jpg. Okay, cool. So this is working the way we want it to work. But there's one issue here. This function, the variable img, where we put it, is actually only visible to this function. So as soon as the function returns, it's not loaded anymore. So what we need to do is add, we can make it public or private. We only need it to be private for the moment, and you can look up the difference later. So I'm going to add a private property called image. Actually, I'm going to call it original image. Okay? So I'll hit save, and I'm going to scroll down to where that is. and it's gonna, I tried to put it in something called original image. When I hover over it, it says there is a property named that. Did you mean to reference it? And if I say, oh, well, yeah, I did actually. Please fix it for me. It says, oh, okay. You need to add the app dot original image in order to load it to the right place. So that's kind of the prefix you need to put, app dot, and then whatever you call the property. So now, what's cool about this is that I can add other buttons and that do other things. Like, let's just, for example, take the derivative, and I'll put this here, resize it a little bit, and let's call it DER. I'll save that, and I'm going to add a push or a button pushed callback, and that's just fine. You can call it that. Okay, so it added the function to handle that. So all we have to do is say, all right, DER, why don't we just call it D equals, now we just remember the name of our function, which I believe is DDR. Let's take a look here. Yep, DDR. Okay. DDR app dot original image. Good. And maybe we want to put this in figure 2. Image SC of D from 0 to 1. And I think we needed to multiply by 5, I think it was, just to be able to see things a little bit better. So we'll do that. So now, when we run this, this is kind of neat. mug1.jpg, we can load the image. Uh-oh. We forgot. My bad here. App.image, that's how we plot it. Let's save that. And actually, I think let's try it again. I think we have to reload it. Yeah. So I'm going to kill this. So it's not running anymore. And then run. mug1.jpg. Alright, let's save. Make sure that everything's closed having to do with this. And that we're not debugging anything. Okay. Oh, that's what's going on. Called it original image. That was the issue. Okay. So I said run. This should work. mug1.jpg. We'll load it. Put that over here. Take the derivative for us, please. And it did. And it does. So, like I showed before, there's lots of really cool things you can do, and the sky's the limit. It's all up to your imagination, and tons of things online. Like I said, I'll just point out what the book looks like that I'm talking about. If I go to Amazon, well, we'll just say Machine Vision Davies. You can see this is what my version of the book looks like. I think there may be a newer
a newer version of it. I think mine's the third, so the fourth, yeah, the fourth looks a little bit different. But it's a little on the expensive side, but massive book, fantastic text, and it goes obviously a lot deeper than my little 2-hour seminar here. So that's all I think I'll say about image stuff. But apps are a fantastic way to kind of abstract things so that any user can go and try to use the things that you've been doing. And we've talked about abstraction on a code level, and that's to make it easier, right? And making user interfaces is the same idea. You're just abstracting something even further. More of the details are taken care of for you underneath the covers. So we could add other controls and other things to this, but I think I'll leave it there for the moment and leave it to your exploration. Thank you for your attention, and let's just make sure we don't have any last little bits here to talk about. I think that's it. Perfect. All right. Thank you for your attention.